We now want to turn our attention to the case of elastic collisions. And elastic collisions again have the property that both momentum and kinetic energy are conserved or constant. So let's write these conditions down. And this is the fundamental difference between the elastic and the inelastic collisions. Now, because we have two equations, and the fact that typically the objects are going to bounce off of each other, the archetype problem, what will typically be given is the initial velocities of both objects, and then it's up to us to find the final velocities. So we have two final velocities, and hence we need two equations. And in one dimension, we need both of these equations. If we're working in two dimensions, say I have an object and it comes in, they bounce off of each other, and they both move off at different angles, then I can use the momentum condition in the x direction and the y direction, for instance. If those are the only unknowns. That's assuming I know both the angles that the objects come off with. But in general, the typical problem is that I know the initial velocities, and then in one dimension, then I'm looking for the final velocities. So let's do a typical problem here, and we're going to start out with the assumption that the masses are the same. This simplifies the math a little bit. So let's say that I have two objects, possibly billiard balls, and let's make that guy a little bit bigger. All right, so we have two objects and they have the same mass. They're both of mass m. And again, I'll call this ball 2, we'll call this ball 1. And the initial velocity of ball 1, we'll just call it v. And the initial velocity of ball 2 is 0. So ball 1 is going to come in and they're going to collide. And we want to know what's going to happen to the system. What is the final velocities of each object going to be? And so we have this guy moving that way. So what we do is we set up our conditions for the conservation of momentum and the conservation of kinetic energy, and then we solve for our two variables from there. Again, the variables we want are v1f and v2f. All right. So in using the conservation of momentum equation, what we do is look at the initial momentum, and all of the initial momentum is wrapped up right here. So pi is going to equal mv, technically mv1i, right? But v1i equals v. And this is going to equal the momenta of both objects after the collision, and we don't know what they are. We're looking for those, so this is going to be mv1f plus mv2f. So both objects could potentially have some velocity after the collision, and it is the velocities that we're looking for. And again, we only have one equation here, but we have our two unknowns. And so we need to incorporate our second condition in this case, which is the conservation of kinetic energy, which says that 1/2 mv1i squared is equal to 1/2 mv1f squared plus 1/2 mv2f squared. And here are our two equations. Right? And we can simplify some things. We can say that m's all cancel out. And in our kinetic energy equation, we have 1/2s everywhere. And so our equations essentially boil down to v1i equals v1f plus v2f, and v1i squared equals v1f squared plus v2f squared. And so, if I erase the leading terms here that we've canceled out, leading factors I should say, we see something rather interesting. And this is a condition that holds specifically for collisions where the masses are the same, and that is that, let's look at the second equation. I have the sum of two squares equaling the squared of something else. This is essentially the Pythagorean Theorem. A squared equals b squared plus c squared, or c squared equals a squared plus b squared, however you want to say it. But essentially, bottom line is that I have something squared equaling the sum of two other things squared. What this implies is in pool, if the collisions are not head-on, if the collisions are not directly head-on, then the pool balls must move off at right angles to each other. The paths of the balls after the collision must be perpendicular. This is not true for the head-on case, which is what we're doing, but when you look at it in two dimensions, what you'll find, if the collision is truly elastic, then the balls will move off at 90-degree angles. They'll be perpendicular to each other, all right? And that's what this equation implies. So now I've simplified my situation here, and I'm going to substitute V for V1I. And now using these two equations, I want to find V1F and V2F. So one of the first things that I can do is solve the first equation for either term, V1F or V2F, it doesn't matter, and then I'll plug that into the second equation. So if I solve my top equation, let's solve it for V1F. I get V1F equals V minus V2F. And now I want to square this and insert it into this equation. Okay? I want to square it and insert it into this equation. So I'm going to get V squared is equal to V1F squared, but V1F is V minus V2F. So if I square this, I'm going to get V squared minus 2 times V2F times V plus V2F squared plus this V2F squared. Okay? So all of this is just this squared. If I square both sides, then I get this. All right? So then I have this left over, so I have to add it in there. So then this becomes V squared minus 2VF times V plus 2 V2F squared. And now, what we can see is that I have only V2F as my unknown. So I've essentially eliminated V1F. And I can get rid of these V squareds because they're the same on both sides. If I subtract one from the other side, it'll be 0. And I have negative 2VF times V is equal to 2 times V2F squared. So if I simplify this equation now a little bit more, this is all going to equal 0. And I can now divide by 2. I can get rid of my 2's because they're everywhere. And now I have a quadratic equation. All right? I have a quadratic equation. And one of the things that I can do at this point is I can divide through by a V2F. Now, I know what you're thinking. I shouldn't divide by 0, and I shouldn't. This is a quadratic equation, and I have two roots. All right? One of them is obviously 0. All right? If I put in 0 for V2F, this is V2F. If I put in 0 for V2F, then I'm going to get 0 identically on both sides, and that is a valid root. But what happens if I divide by the other root that by assumption is not 0? So if I divide by that root and don't get a 0 and I get a valid number, then I know that that is a valid root. So I'm going to divide both sides by V2F, and I get that V2F, well, let's move this term over here first. So we're going to get V2F times V is equal to V2F squared. And so I divide by my V2F, and I get that V2F is equal to V. This is an astounding result. V2F is the final velocity of my second ball is equal to the initial velocity of the first ball. So what is the velocity of the first ball? Well, if I look at my first equation here, I have V here, and now I have V here. V1F must be 0. So V1F is 0. What this implies is that as my two objects collide, my first object comes in, they collide, it stops, and the second moves away at the same speed. It does this. And this is in fact what we observe. If you go to a billiard table and you hit a billiard ball dead on with the cue ball, the cue ball will stop and the billiard ball will keep moving. So intuitively, this makes sense from the experience that we have, but it's rather astounding when you actually stop and think about it. What's happening is that as the two objects collide, as they collide elastically, all of the initial object's momentum and all of its kinetic energy gets transferred to the second object. And so because all of its momentum and kinetic energy get transferred to the second object, it has none left over. It has nothing with which to move. And so the second object moves off at the original velocity after the collision, and the first ball stops. All right? So there's your introduction to elastic collisions.